Alright, hey guys, what's going on? So today we are going to be talking about symmetries of the Riemann tensor. In the last video we started to talk about the geometry of the Einstein tensor. We're going to use the symmetries of the Riemann tensor to then discover some things about the Einstein tensor, and then from there we're going to go into more of the physics of things. We're going to start looking at the stress energy momentum tensor and diving deep into that. So without further ado, make sure to hit my like and subscribe button, and make sure to go onto my Patreon page as well if you want to support the channel. I'm happy to see that this channel is slowly but surely gaining popularity, which to me says a lot of you guys are dying to really want to understand physics. So without further ado, let's get straight into the topic. So today we're talking about the symmetries of the Riemann Curvature Tensor. So we've talked about everything up to this point. Now let's get into the deep end with some of this stuff. There's two tools that we're going to use to talk about the symmetries of the Riemann tensor. The first tool is going to be this idea of metric compatibility, which is something I go over in my tensor calculus playlist, and something called torsion freeness. And this is to say that the connection is symmetric about the I and J index here, okay? And these two ideas are really foundational to classical GR, right? These two ideas are broadly assumed for most everything that we do in GR. This starts breaking down when we start talking about quantum gravity and stuff like that. So, and that's going to be in the playlist on quantum gravity. So we're not going to focus on, we're sort of going to take these at their word for right now. If you want to see them in more detail, you can go into my tensor calculus playlist, and we might get to these concepts later in more depth in this playlist. So the first symmetry is this symmetry here when we swap the first two indices, so mu and nu, and the way we get this is we say, well, this is the definition of our Riemann tensor. Our Riemann tensor, as we've talked about in my tensor calculus playlist and in this playlist, is the difference between going traveling on a manifold in one direction and then another, and then doing that in the opposite order. So in the mu order and then in the nu order, or in the direction, right? So this should be a direction. They are vectors, right? But the idea here is that they are vectors within a tangent space. And so this is in the mu direction, then in the nu direction, and then the nu direction and the mu direction, and then we have this added part here. We're not really going to concern ourselves with this added part right here, just because a lot of this is just going to cancel. But this is part of the definition of the Riemann Curvature Tensor. If you want to understand this more, just sit tight. I'm probably going to get into a video on this later on. But for right now, we don't really need to know it in too much depth. And so now we define it now going in the opposite direction. So in the nu and then mu, and then mu in the nu direction, and then we swap these guys as well. Well, this guy here is just the negative of this guy. So when we could say that this guy here is the negative of this guy. So it's anti-symmetric with respect to the first two indices, so mu and nu, okay? It's also going to be anti-symmetric with respect to the alpha and beta indices, and we'll see that coming up soon also. But let's go over the second symmetry. Second symmetry is concerning the three indices here, okay? And this is something that we're going to use quite a bit. The idea here is that we swap the indices. We do this permutation, right? So E alpha, and then E alpha is out here. Okay, so the E alpha keeps on moving this way. Same thing with E beta, keeps on moving this way, and when it gets here, it comes to this point, right? So here's our E beta, and then our E beta, and then our E mu, and E mu. So we are cyclically permuting these entries, right? So again, two entries here are the vectors that we input which represent the directions by which we travel on the manifold. And then what we're doing here is we are now substituting the definition of these guys in terms of their covariant derivatives. And when we do that, we see that these green guys will cancel, the blue ones will cancel, and the red ones will cancel. And these are all just basis vectors. So this is in the E alpha, E beta direction. And the commutation of a basis vector, well, that means this is just going to go to 0 because they're, again, basis vectors. And so what we get is this relationship right here. So the two relationships that we have now are anti-symmetric in the first two indices. We have this symmetry in the last three indices. Now let's take a look at the last two indices, right? So the idea here is that, because we're going to come to this point, right? But before we do that, let's get started. So this is quite big and nasty looking, but we're going to dissect all of this. So the idea here is we're going to be using metric compatibility. So we have our Riemann Curvature Tensor. This is the definition right here. And we're applying this on an inner product between two arbitrary vectors, R and S. Okay, here's R and S. So, okay, so let's go ahead and start. So this is going to go to 0 because we have basis vectors. All right, so the commutation again of two basis vectors, well, that goes to 0. So we're left with distributing everything out like this, and then we can distribute even more, right? So this is E beta acting on R, and then the whole thing acting on S, and then same thing, E beta. So this right here. So E alpha is going to act on all of this. So this E alpha is right here. This right here is derivative of R times S, and then derivative of S times R. That's all of this. We're doing the same thing right here. All right. And then we can break this up even more, right? So we have E alpha. So all of this is right here. And then this guy with this E alpha is right here. And again, we're just breaking all of this up. So we get this and this. All right. I was careful to put all of the indices in the right place. If you catch something, write something in the comments. Please let me know. But this is how all of this is playing out. So this stays the same. So all of this really stays the same. What we're doing in this line here is we're really just applying this next derivative, right? So E alpha is going to be applied to R, and then it'll be applied to, here, I'll draw this out, right? So E alpha is going to be times this, not times that, right? This is, so this guy here, we're going to take the derivative of this and multiply it by this. And then we're going to take the derivative of this, taking this, the derivative of this, E alpha, right? So the idea here, again, is that's going to be right here, right? Because that's a second derivative for S. And you can kind of see how this all plays out, right? And then we have, for this guy, this is going to be E beta E alpha times R, or so the second derivative of R, right? So that second derivative right here, right? And then we're going to have another second derivative, right? Because we have this second derivative, which is showing up right here. And then all the single derivatives are in there as well. Right? So what we get is this big, long, ugly thing, these two lines. And then we can see we cancel things out. So everything that doesn't have a second derivative, essentially, gets canceled out. And what we end up with is second derivatives on R, second derivatives on S, and then dot product with S and R, respectively. Okay. And then, so what we can say is that, well, this is the Riemann curvature tensor, because that's a definition. This is Riemann curvature tensor, because that's definition. And that's, so here's our Riemann curvature tensor, here it is again, applied to S, applied to R, and then dot product with S and dot product with R. Alright. So now, let's deal with this side of the equation. This side of the equation, again, is the R, so the Riemann curvature tensor, again, applied to the inner product. Well, that's going to be 0 because this is just the inner product is just a number. It takes two vectors and it applies a number, or it creates a number out of two vectors. And so the double derivative of just a number is going to be 0. So that's where we get this 0. Now let's jump back to this side. We're saying that 0 is equal to this right here. So we're now saying that R is a basis vector and S is a basis vector. All right, so R is this basis vector and S is this basis vector. Okay, so now we can, sometimes the computer program I use here gets this new here and this new here are different sometimes, but they're the same. They're the same thing. Okay, so now our Riemann curvature tensor, these are alpha and beta. These are the two input vectors that we're defining our directions with in the tangent space. All right, and then E mu is going to be the index here. That's the vector that we're traveling with on our manifold. And then we're going to put our I to identify the output vector. Okay, so the I identifies the output vector. We're doing the same thing right here. Okay, identifying the basis vectors necessary, and then we have E nu, and then this whole thing is a vector with EI being the basis vector. Same thing here. Okay, so hopefully that made sense, right? So this here is this right here. Okay, all of this is this right here. All right, and then the rest we say, here's our EI and EI, summing over EIs and EIs. And then we don't want to forget these guys. Okay, so those are these guys right there. All right, so now what this enables us to do, I can erase a few things. What this enables us to do is say, well, here's our Riemann curvature tensor. Here's our Riemann curvature tensor. Here's our E mu and our E mu. Here's our E nu and E nu. We can take out the EI. We can take out the EI here. And so, I'll erase a few things just to clean things up. These EIs are just, we're bringing them outside of the parentheses there. So we get these inner products right here. These inner products are just the metric, right? We talked about the metric being the inner product of basis vectors in the tangent space, which makes it a metric space. And then we have this sum over the i's. We drop the indices because that's something we've talked about also in our tensor calculus playlist and in GR. And we get to this point right here, and we can see that mu and nu and mu, they're inverse. So there's anti-symmetry with respect to the first two indices as well. So anti-symmetry with respect to the last two indices and anti-symmetry with respect to the first two indices. The next thing we want to do is discover this fourth symmetry in our Riemann curvature tensor. So here we start with this right here, right? We're just moving things to two of these guys to one side of the equation to get this. All right, we can then flip variables again because we have anti-symmetry with respect to the first two indices, anti-symmetry with respect to the first two indices again. And then what we do is we can recognize this guy here and this guy here gets split up into those according to our second symmetry right here. All right. And then we see that this guy and this guy can get bunched into here, right? Because we can just flip the mu and nu again. That gives us positive, which is where this 2 comes from. And then we have we can flip again our indices to get these two guys. All right. So I'll erase some things just to clean things up. Now we get to this point here. We get to this point right here. Because this, again, is just this right here. So these and this guy. Because, again, we have the beta, beta, and beta. So we're just permuting the last 3 indices. Right? You can see how this is like really, really helpful. Because it enables us to expand things and then condense things down. So exploiting these symmetries is going to be key in doing practice examples that we will go through later. But again, the idea here is that we really are exploiting these symmetries. We discover them and then exploit them. So we get this. And this, again, recall, was all equal to this guy up here. So we just drop this guy back down here. And then we say, well, we can add this to both sides, right? We add this to both sides, bring it over here. That makes it positive. Okay. And then we have so if that's positive, that's going to be 2 on the side and 2 on the side. And then we get to this right here. So this is our other symmetry here, right? The other symmetry is if we swap these two as a group, we have symmetry. Okay. One thing to point out here is that when we're doing all of this symmetry, so we have all of these symmetries at our fingertips now with respect to the Riemann Curvature Tensor. One thing to keep in mind is that if you were to picture this as a matrix, say, we have we can have this as R, mu, nu, alpha, beta. We can sort of picture this as some sort of four-dimensional matrix that has a lot of indices, right? We have, so one way to do this is if we hold mu and nu constant, for example. So say 0 and 0. This is a 2 by 2 matrix now, just with the first 2 indices being 0. We have another matrix we can identify as R11A alpha beta. And then we have another one, another matrix R22 alpha beta. And you could see where this goes, and then we could have R02 alpha beta, right? And so forth, right? We can have R12 alpha beta. So all these symmetries help us in not having to think about all these matrices, right? We say, well, if we know what say, if we have, say, R00, here, I'll write it like this. If we have R0012, that would be this entry here. Well, R0021 would be right here. how are these guys related to each other? Well, that's the last two indices. The last two indices are, that's what happens when we, in this symmetry right here. Right, so they're negative of each other. They're anti-symmetric. So this is just minus 1, 2. Right? And we could play this game for a few others, right? So we can actually play this game for this guy if we can. Let's actually do it for this guy because this guy's quite interesting. Say we had R1, 0, 2, 3. Say 3. Well, so this is going to, so mu nu is going to be 2, 3, 1, 0. Right, so you can see now how R1, 0, I will erase these matrices. All right, R1, 0 R1, 0, 2, 3. That's in one matrix where we've identified constants 1 and 0. But then in another matrix, somewhere way over here, we have R2, 3, 1, 0. So in this matrix over here, this is actually the same value. It's going to be the same value as the entry in the matrix over here. Over here. So this is why these symmetries are super, super important and super useful, is because they help us really narrow down the degrees of freedom of the Riemann curvature tensor. And what things end up turning out to be is that the number of degrees of freedom in the Riemann curvature tensor is actually less than if you just thought that these were all independent variables. If each and every one of these, if there was no symmetry here, we would have a total of 4 times 4 times 4 times 4 independent variables. And that would be like something like 256 independent variables or something like that. But this gets massively reduced because of all the symmetries. So with that being said, I hope you guys enjoy this type of content. Make sure to hit that like and subscribe button, and make sure to go into my Patreon page if you want to see notes and support the channel. So I'll see you guys in the next video.